Welcome to the Ontario High School video podcast regarding chemical equilibrium. This will be part one. The issues we'll be dealing with in this podcast are primarily what to do with the equilibrium constant, K sub C and K sub P. Till this point in chemistry, we primarily have looked at chemical reactions as going in one direction. We put some reactants together. We learned from kinetics that the reactions are based on collisions. The reactants collide and products form. Unfortunately, life's not that simple in the chemical world, and many reactions do not just continue in one direction, going from reactants to products, but the products are colliding in the reaction system as well, and the reverse reaction can occur, and often does, to where the products collide with either reactant molecules or other product molecules, and the reaction can go the reverse direction. And one of the ways that we'll show this in the chemical reaction equation is by showing a double arrow. So here we have the equilibrium reaction of hydrogen gas reacting with oxygen gas to form hydrogen iodide gas, and the double arrow in the equation indicates that this reaction does not go 100% to completion in the forward or rightward direction to form hydrogen iodide, but a dynamic system in which the forward and reverse reactions will come to take place at the same rate. And the key there is that the reaction is taking place forward, for instance, hydrogen and iodine molecules colliding to form hydrogen iodide at the same rate that hydrogen iodide molecules are colliding and decomposing to hydrogen and iodine gases. The key is that the rate of the forward reaction equals the rate of the reverse reaction when equilibrium is achieved. It does not mean there are equal amounts of hydrogen iodide and the reactants hydrogen iodine. It just means the rate at which the product is being formed is equal to the rate at which reactants are being reformed in the reaction. Want to emphasize again that when the reaction system is at equilibrium, HI is forming from H2 and I2, the forward reaction, at the same rate that HI is decomposing to H2 and I2, which is the reverse reaction. It is the rates that are equal, not the concentrations, but the rates. One more time for emphasis. Equilibrium does not mean equal amounts, merely that the rate of the forward reaction is equal to the rate of the reverse reaction. This is a very strong misconception among many, that the word equilibrium means equal amounts. It is not equal amounts. It is simply an equal rate of the forward reaction and the reverse reaction happening simultaneously. In order to evaluate equilibrium systems, one of the things that we have to do is to be able to write a mathematical expression that relates what is occurring in the system. So this equilibrium constant expression, also known as the law of mass action, and what it is it's a ratio of the molar concentrations of the products raised to a power equal to their stoichiometric coefficients divided by the product of the molar concentrations of the reactants raised to a power equal to their stoichiometric coefficients. Now, that is when we're dealing with a K sub C using the molar concentrations. This can also be expressed if all the reactants and products are in the gas phase using pressures as well as concentrations, and we'll talk more about that later. Let's take a look at a generic chemical reaction and see how we would write the expression for the law of mass action, or the equilibrium constant expression. Here we have a chemical reaction in which A, B, C, and D are the reactants and products. W, X, Y, and Z are their stoichiometric coefficients. So here we have K being equal to, in this case we're using molar concentrations, so we have the molar concentration of C raised to Y times the molar concentration of D raised to Z divided by the molar concentration of A raised to W times the molar concentration of B raised to its stoichiometric coefficient as a power x. Returning back to the chemical reaction that we examined earlier, here we have hydrogen gas plus iodine gas yielding hydrogen iodide gas in an equilibrium reaction. The law of mass action or equilibrium constant expression for this will be K is equal to the concentration of hydrogen iodide, which is the product, squared, divided by the concentration of hydrogen gas times the concentration of iodine gas. Let's look at an equilibrium system in which a just very slightly soluble solid is dissolved in water. Here we have lead 2 chloride being dissolved, and when ionic compounds dissolve, we know that they separate into their constituent ions. So for lead 2 chloride, when it dissolves, the lead 2 plus ion is in aqueous solution, and then we have 2 chloride ions for every formula unit of lead 2 chloride that dissolves. When we write the law of mass action or the equilibrium constant expression for this, you'll notice it's a little different than what we've done previously because the reactant isn't shown. Okay, so here we have K is equal to the concentration of the lead 2 plus ion times the concentration of the chloride ion squared. Note that the solid reactant, lead 2 chloride, is not included in this equilibrium expression. For this reason, pure solids and pure liquids such as water are not included in equilibrium constant expressions because their concentrations do not change. When water is present as a gas, as a vapor, it is included, but liquid water is not, and pure solids are not included. Depending on the textbook or problem writer, K will often be expressed with a subscript indicating whether you're dealing with concentrations, molar concentrations, or dealing with pressure, or a solubility product, or an acid or base. So let's just take a look at those real quick. If you see K sub C, this is used when the concentrations of the reactants and products are expressed in moles per liter or molarity. When you see K sub P, this is used when the pressure of reactants and products are used in the equilibrium expression. And we've been looking at the reaction hydrogen gas plus iodine gas reacting to yield hydrogen iodide. So here would be expressing that in terms of their pressure. So here we can see the square of the pressure of the hydrogen iodide divided by the pressure of hydrogen times the pressure of iodine, a K sub P rather than K sub C. KSP is used for solubility product equilibriums, and the previous reaction that we looked at in the slide just before this, which showed the dissolving process of solid lead 2 chloride going to lead 2 plus ion and chloride ion, that would be a solubility product equilibrium represented by KSP. Ka or Kb are used in acid-base equilibrium systems, and we're going to explore acid-base equilibrium systems in a future podcast, but when you see Ka or Kb, that's what that is referring to. Still talking about the equilibrium constant K, and whether it's K sub C, K sub P, KSP, Ka, or Kb, it's really important to remember this. The equilibrium systems and the value of the equilibrium constant K are temperature dependent. The value of K is stated under specific temperature conditions. The value for K does not change unless the temperature changes. So when you see problems involving equilibrium, if a temperature isn't expressed, they're giving you a value though for a fixed temperature. If they don't express the temperature, they're implying that the temperature of the system is not changing, so the value of K for that should not change. If the temperature is changing, they will have to give you in the problem the two different temperatures that you're evaluating things at, and then you're normally directed to use that in some way to show how K changes because of temperature. But depending again on the textbook and whoever writes the problems, when they give you a value for K and they don't state a temperature, just accept that that value is K and that the temperature isn't changing. If temperature changes, K will change. If temperature remains constant, the value for K will not change. Well, let's write some equilibrium constant expressions or law of mass action expressions. I give you A through E here, different reactions that are equilibrium reactions, and that's shown by the double arrow. This would be a good time to pause the podcast and write these equilibrium constant expressions, and when you come back and proceed with the podcast, I'll show you the answers. So let's see how you do. Good luck. Welcome back. Let's see how you did. The first reaction was the reaction of nitrogen gas and hydrogen gas to form ammonia, or NH3. Remember, when we do an equilibrium constant expression, and this one we're doing in terms of concentrations, so we would have the molar concentration of NH3 squared divided by the molar concentration of N2 and the molar concentration of H2 cubed. So check and see how you did. For B, we want the K sub P expression for the reverse of this reaction, which is NH3 decomposing to form nitrogen and hydrogen gases. In this case, we'll have the pressure of N2 times the cube of the pressure of H2 divided by the square of the pressure of ammonia. C, you were asked to write the solubility product expression, equilibrium constant expression, for the dissolving of lead-2 iodide. And remember, we do not show solids in equilibrium expressions, so here KSP would be equal to the molar concentration of the lead-2 plus ion times the molar concentration of the iodide ion squared. For D, we have the thermal decomposition of calcium carbonate, and we know that when calcium carbonate decomposes, like all carbonates, the thermal decomposition yields products of calcium oxide and carbon dioxide gas. The calcium oxide is a solid, the calcium carbonate is a solid, so in this equilibrium expression, the only thing that would be shown is the product that is gaseous. And here, because we're looking at the concentration, you would show the molar concentration of carbon dioxide. So K sub C would be equal to the molar concentration of carbon dioxide. E, we ask you to express the equilibrium constant in terms of pressure for this same reaction, so you would just show K sub P is equal to the partial pressure of CO2. This is the end of part 1-1 of the Equilibrium podcast series here at Ontario High School. I'll leave you with a quote from Mark Halperin. "A lot of people hate heroes. I was criticized for portraying people who are brave, honest, loving, intelligent. That was called weak and sentimental. People who dismiss all real emotion as sentimentality are cowards. They're afraid to commit themselves, and so they remain cool for the rest of their lives until they're dead. Then they're really cool." Stay tuned for part 1-2.